Mm-hmm. Right. Not just for BEQs, but even for like other instructions. Have you tested that?
Yeah, but I don't think that, I think that if you have an LW on a undefined global variable, it should function correctly and just
Yeah.
set it to
What
zero
happens if
though.
there's duplicates? Are you going to insert them in your table twice,
No,
or like I mean I'm just
I
asking.
only have it once because
Okay.
I basically, the way I've
All
done it
right.
is probably different from everyone else because it's the most disgusting implementation. I've created nearly 30 arrays and filled them
Okay.
so I can constantly see every.
Yeah.
I'll interject, guys, but we can continue to take a closer look at what might be going on. But we'll get started with today's lecture. So we are going to be continuing our processor discussion. Yesterday we talked about um, single cycle processors and how we can basically have something, a very simple collection of combinational and sequential logic devices that can be combined together and execute our programs. So we're going to continue that and talk about enhancements that we can be making to this design, since what we designed yesterday, while functional, is not going to be very practical, and we'll talk about why. So homework 3 is posted. That's due next Tuesday. Discussion posts are not going on today, or not going on tomorrow, but they're just going on for the remainder of today. Project 2 is posted. If you didn't see the announcement, we pushed back part 2A, that deadline, back one day. Note that we're not pushing back the remaining parts of the deadline. So although, yay, we're getting one more day for this, that's effectively one less day for the other parts if you are taking that full day to keep working on 2A. So just be cognizant of that. If you're able to get it done and start moving on the other stuff, we really encourage you to do that. We're really strapped for time in the spring semester. The final project is literally due the last day of class. I'm not allowed to have assignments due after classes have ended. So we really don't have room to shift everything back. It's just kind of, what are we compressing and what are we expanding in other parts? So just be aware of that. We have the remaining parts listed out there. Any logistical questions before we hop in? All right, so as I said, last time we discussed the single cycle processor. We saw how to implement these basic operations, as well as briefly talking about jump and link registers. I'll kind of refresh on that since we kind of rushed through it a bit. This was the basic organization of what we came up with. And we saw that by having memory, register file, and a bunch of muxes. Muxes are really the lifeblood of this processor, of taking a bunch of things that are kind of simple on their own right, throwing a bunch of muxes in allows us, by controlling it via a control ROM, to do a very diverse set of things. And so we saw that for the add instruction example. We went through all the instructions, what we set the control ROM to. So go back, look through those if you want any more clarification, but I'll just quickly redo the add instruction so we're up to speed. If I'm figuring out how to control each of these red lines coming up, this is controlling how data is moving through the data path and what operations we're doing. Well, the ALU, we said that we defined this ALU such that a 0 going into the control input will do an addition, a 1 will do a NOR operation. So that's obviously going to have to be 0 to do that add. We're using the destination register as the index. So as a reminder, these are all indices here. These two are the read indices. This is the write index, and then this is write data. And then this is write enable. So the write index, we're going to use the destination register, which is the bottom input of this mux. So that's going to have to be a 1. The data that we're writing into the register file is the result of the ALU operation. So we want to take this guy, wrap it around, and we're taking the bottom input of the mux. So that should be a 1 there. We are writing data to the register file, so that 1. The stuff that we're writing into memory is, this is the second operation, the second operand going into the ALU here. And that is intended to be the second register that we've read out, register B's value, not the offset, which would be used for loads or stores. So we want this to be A1 to select the bottom input. And then we're not using memory at all, so we'll disable it by setting the enable to 0. And it doesn't matter what we set for read or write because it's disabled. So either one is not going to do anything. So when we set up our control ROM, we need to design it in such a way that when we pass in 0, 0, 0, which is the opcode for the add instruction, it spits out these 4, 5, 6, 7 values. Any questions on this before we go on? If you have misconceptions about how this works, you're probably going to be lost for the rest of this lecture. So now's a great time to ask any questions.
Can you explain how the decoder then tells the ROM how to set which inputs?
Yeah, so the decoder is set up. We kind of talked about that briefly last time. Let's see if I can hop forward to some slide that has this. It's further back than I thought it was going to be. So we end up having something like this. This is a ROM that we can control to set out specific things. So as a reminder, the decoder, when we send in a specific binary value, it will set out the line number. It will set that high. So if I have 0, 1, 0, 0, that's going to be a binary 2. So it's going to set the 0th 1 second row high here. This is going to go high. And then we can program what the output is by putting little diodes in here, such that if I set this to 1 and this to 1 and then leave all the other ones not connected, then this ends up reading out 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0. We're going to use this illustration as a way to show how we're programming this ROM. It's not really that important for you to understand exactly how this is operating at a hardware level. You can take a look at the previous slides where we had the diode drawing if you just want to read and digest that a bit more. But basically, just by putting dots at strategic locations here, we can have this read out arbitrary data for any given input. But it's totally fine if you just want to think of this as being a hardware table that spits out data when we send in an address. Okay, so again, I briefly shot through the jump and link instruction last time. Jump and link register instruction is the ugly instruction of this instruction set. And so we got to add a bunch of extra data path and logic gates in order to get it to work. We're really not going to focus on it after today, but you should be aware basically how it's working. We said that we had to add an extra mux into the PC since we need to be able to take the result of the register file, since we're taking register, one of these registers, the value, and storing that into the PC. And then we need to have an AND gate that detects when this is a JALR instruction. So we just look at the opcode. If those are specific values, then we'll set this to true. This is detecting if branches are, if this is a branch instruction and if it's equal. So by setting these inputs to the mux accordingly, we will grab the correct value from the multiplexer. The other weird thing about the jailer instruction is we have this kind of weird property, if you remember from the spec, that if the two registers are equal to one another, first it updates, what does it do? First it updates or stores PC plus 1 into the destination register, into register 1, and then it reads register 1 and puts it into the PC, which basically has the effect of we just branched to PC plus 1, meaning we didn't actually branch anywhere, we just went to the next instruction. That's how it's supposed to look from the programmer standpoint. But if we just kind of do this the naive way, PC is going to be updated at the end of the clock cycle. Anything in here that's this light gray color is a clocked input, and that means that it's going to get updated at the end of the clock cycle. But in theory, right, we're supposed to anyways, it's, if you work through it, you'll see that it's not going to work the way that we immediately want it to. So we have to put in explicit logic here. Basically, if we detect that these two register indices here are equal, so this NE stands for not equal. So if they are equal, then we should go ahead and disable this and say, no, ignore the jump instruction. Just go to PC+1 like normal. If they're not equal, then we can treat this like a normal jump instruction. So again, we're not really going to focus on implementing the jailer instruction just because it adds a lot of complexity and tedium to working through these problems. And if you understand how all the other instructions work for the different architectures that we're going to go over, then you're fine. But I just wanted to include this here so that you knew how we would extend this in practice. What's the blue arrow going into the mux? So right here, this is PC+1, because we're saying in this case, the two registers are equal to one another. So I want to ignore this jailer instruction in terms of incrementing the PC. I'm deactivating this, so both of these are 0, and we're selecting the top input, which is just PC+1. That's what this circuit here is doing. Oh, sorry, you're talking about the register file. Yeah, so that's this is the same value. So anytime I have two arrows that are the same color, like over a distance here, that means that I'm somehow connecting those. I'm not literally drawing a line everywhere because that would just crowd everything up and make it hard to understand. But that's what that means there, that there's an invisible wire connecting those two blue wires, because we need to store PC+1 in the register file for the jailer instruction. Okay, so you went through last lecture, you said, okay, cool. We've got a working processor. We can implement all the instructions now. Yo teach, why do we still have half the semester left? Well, it turns out there's a lot lacking with this single cycle implementation. It's called single cycle because we just have one clock tick where we fetch the instruction, pass it through the decoding, that control Rom. We read the register values, pass it through the ALU, store or load the result from memory, update the PC. This is all happening in one clock cycle. And the issue with this is that not all instructions are running at the same speed. And remember that we have to set the clock frequency in order to accommodate the slowest path, which in this case would be the slowest instruction. And so if we just add in a single instruction that has long latency, like if we did multiply, even if we did it in hardware, not like software like you did in Project 1M, that's going to be time consuming to do it in hardware. It's basically going to have to do all of the same shifting operations and additions together. It's going to take a lot longer than just adding two binary numbers together. And then if we were doing the single cycle design, we would have to really increase the clock period. And that just makes every instruction take longer because we have to prepare for the worst case scenario. There's also a few other issues. We have 3 different adders. Adders are kind of expensive. This was particularly critical in the olden days of computing when space was really a prime resource that we couldn't waste. So it doesn't seem ideal that we have 3 different adders, especially when we're using them at different times during the clock cycle. PC+1 we can increment right at the beginning. A little bit later we're incrementing PC+1 with the offset. A little bit later we're doing the ALU, and just why we have all this going on. So yeah, we're not really doing a great job of this mantra of computer architecture of making the common case fast. I'm going to be doing a lot more adds than multiplies most likely, so it seems silly that I'm making my add instructions longer in order to accommodate something like a multiply instruction. Let's do a quick little exercise and just kind of motivate this a bit more. So let's say that it takes 1 nanosecond to read or write to a register, takes 2 nanoseconds to do an ALU operation, 2 nanoseconds to do a memory access, and then all these other components, let's just say, ignore them. They're 0 nanoseconds. So for an add instruction, we have 2 nanoseconds. We have to, every instruction always has to read the instruction from memory. So all of them will have that factor. So we have 2 nanoseconds there, 1 nanoseconds to read the 2 registers. Then we add them together. That's going to take 2 nanoseconds. We don't have to do data memory for an add instruction, so that's fine. But then we have to go back and again access the register to write the result at the end. So that's going to be a total of 3, 4, 5, 6 nanoseconds. If we do a NOR operation, going to be very similar, right? In fact, it's going to be exactly the same. We're just doing a NOR operation instead of an add operation with the ALU, but we're assuming those take the same here. For a branch if equal instruction, again, we have to read the instruction, read 2 register values, and do an ALU operation to compare them. Well, not to compare them, but to calculate the branch offset if necessary. We don't write anything to memory. We don't have a destination register, so that's a little bit faster. I'll open up a quick question to you. What is the latency going to be for load and store word instructions? Let's take about 30 seconds for that one. Let's take 10 more seconds. Three, two, one, and close. Yeah, so let's think about this. So for store word, always we read the instructions. That's going to be 2 nanoseconds. We do have to read the register that we're reading as well as the memory address or the offset. We have to add those 2 together. And then we're doing a memory operation here. So that's going to be, 2 nanoseconds. And then we're not writing anything for a store into the register. So that's going to be 2, 3, 4, 5, 6, 7 nanoseconds. And then load word is going to be exactly the same. We have to read the instruction, read the values as well as the offsets, add the offset to the base. We are accessing memory, and then also we have to write the value back to the register at the end. So that's going to be another nanosecond. So just 1 more nanosecond than the store word, 8 nanoseconds total. So 7 and 8. And it looks like about half the class had gotten those ones right. Any questions I can answer on that example? Okay, so yeah, in fact, this is probably going to be a lot more exacerbated in real hardware, particularly memory accesses can be really slow depending on the system we're working with. Obviously, yeah, if we're adding more complicated arithmetic operations, if we have floating point operations, that's going to take a lot longer than adding because we have to back and forth, adding them together. Even though here it's only a difference of 2 nanoseconds or 3 nanoseconds between the fastest and the slowest, in real architectures is probably going to be more exacerbated. And the key is that we're always just going to have to set this to 8 nanoseconds in this case, because it doesn't matter even if we're doing 90% branch instructions and only the occasional load word, we have to accommodate the worst case scenario. Zren is asking, is the latency of writing to mem equal to the latency of reading from mem? Yeah, we'll assume that for now. And I think that's a typical abstraction that's at least provided at the architecture level. When you're actually working with like DRAM circuits, it might be a little less clear than that, but yeah. So yeah, let's, as another example, let's say that we're executing 100 instructions. This is the breakdown of how many instructions are which. If I want to figure out how long this takes in my single cycle execution, well, we figured out that 8 nanoseconds was the worst case scenario. So I'd have to set my clock period to 8 nanoseconds, and I'm doing 100 operations. That makes us take 800 nanoseconds to execute. But if I could somehow only have each operation take as long as it needed to, like if I could have a variable clock speed that responded according to the type of instruction we were executing, well, then 25% of loads take 8 nanoseconds, 10% of stores take 7 nanoseconds, adds take 6 nanoseconds, 20% take 5 nanoseconds. That gives us 640 nanoseconds. That's 160 nanoseconds that we're wasting with this constraint that we have to set the clock period according to the worst instruction. So this is strong motivation that we'd like to try and come up with something better, that we aren't kind of holding ourselves to the worst case. We want to do the best case. We want to make the common case fast. We're probably going to be doing lots of these types of operations. As we can see here, the common case is doing these arithmetic operations. We would like our program to go faster when we're doing faster instructions. Seems like a reasonable thing to want. So this is the motivation behind having a multiple cycle processor. And the idea is, rather than having one long clock period to do every instruction, we're going to break up each instruction into smaller subtasks. This is going to reduce the cycle time. Slower instructions are still going to take more time, but they're going to take more cycles. Faster instructions are going to take fewer cycles. And the nice thing about taking fewer cycles is that we can respond at the end of the clock cycle when we're done, and then we can start executing the next instruction sooner. So we're kind of increasing the granularity of when we can start and finish instructions. That's going to be really helpful. And as a nice side effect, this is also going to allow us to reuse some elements and make our overall processor smaller. What is going to be needed to make this work? Well, we're definitely going to need more storage elements. If we're taking more cycles to execute each instruction, we're going to have to remember values across multiple cycles. We're also going to have to reroute from different parts of the design. So we're going to need more muxes, more storage requirements, more registers. And the control is going to be more complicated because we need to keep track of how many cycles in are we to each particular instruction type. So this was our old design. One thing that we can immediately change is I'm not going to need separate adders here for incrementing PC+1 or PC+1 plus offset. I'm just going to reuse this ALU a bunch of times for all those sub operations. We can merge data memory and instruction memory together. And we're basically going to, in our baseline implementation, we're going to break this up into about 3 cycles. In the first cycle, I'm going to read stuff from memory according to the PC address. I'm going to store that address into, or store that instruction into some sort of register to remember it for the later cycles. On the second cycle, I'm going to go ahead and read the values from the register file. And again, store those somewhere. And then on the third cycle, I'm going to go ahead and actually compute the results. And then for some instructions, I'm going to, actually, yeah, we're going to take more than 3 cycles, but this is what we're always going to start off with. And then we'll take another cycle or 2 to write results back, but we'll look at the details of that. But this is the basic idea. We're taking something that used to take 1 clock cycle, and we're breaking up into subtasks.
Yo, Teach.
Yeah, go ahead, Jacob.
So are we thinking of this like when cycle 1 finishes, it's starting a cycle 2, but it's also starting another cycle 1?
Good. So you're jumping ahead a bit. You're talking about pipelining this, which we're going to get to in a couple lectures. But for right now, we're just keeping it simple. We're only doing 1 instruction at a time, but we're just kind of chopping it up into little pieces. Good question, though. Okay, so this is what our multi-cycle data path is going to look like. A few things to see. We have this extra instruction register here. Again, we need to remember the instruction that we're executing for multiple cycles. We have some extra muxes here, you know, particularly right here. It used to be that always register A was going into the ALU. Well, now we're also using this ALU for PC plus 1 plus offset. So we want to take this value into here. And then these are all the control signals for each of these elements. We have a hard-coded 1 in here to handle PC plus 1. Yeah, and we'll go through examples for each instruction to see how all these changes are going to impact the design. But because we're dealing with multiple cycles and each instruction is kind of doing its own thing, it's going to be helpful to think about this as a finite state machine. So get the state diagram, figure out how we're transitioning between each of these states. We're always going to fetch the instruction first. That's the process of getting the instruction from memory, storing it in the instruction register. The state 1 decode, that's going to be looking at the instruction, passing it into the control circuitry to figure out what we're supposed to do. And then we'll split off into a different state machine for each individual instruction. Most of these are going to take 2. Loads are going to take an extra cycle. We'll see why, but it makes sense given that before load word was the longest instruction. And yeah, we'll go through each of these states and see how that goes. Once we get to the end of each instruction, each of these, even if I haven't showed it, has an implicit cycle back to the fetch instruction. So we have this endless process of fetching instructions, executing them, fetching the next instruction. Okay, and so now we're back to our old diagram from before. We need to implement this finite state machine. I have 12 states here, plus 0 is 13 states. Log base 2 of 13 would be, what, 2, 4, 8, 16. So we would need 4 bits to get up to 13. We round it up to the nearest integer. So we'll need 4 flip-flops, 4 bits of states in order to keep track of which of the 13 states on the previous slide I'm in right now. And then we'll have to, yeah, get some Rom like we did last time to figure out what is the mapping of each current state along with the current inputs. And the inputs here are going to be the opcode that we're processing right now to figure out what the outputs are supposed to be. The outputs are going to be these control signals here. And then we also have the next state. And the next state is going to be, again, 4 bits because that's just what we're plugging into the flip-flops. Okay, so now we're back to this picture. And as I said before, every time we have a dot in one of those locations, it's going to signify that when we read this row out of the ROM, it's going to set that bit as high. Anything that we don't have a dot is going to be assumed to be a 0. So our job over the next several slides is to figure out where do we need to stick dots in here to make sure that our control ROM outputs the right results for the output. So these are those MUX and ALU signals over here and enable signals, and then also outputs the right next state outputs. So let's jump into it. So the first state that we're in, state 0, is the fetch instruction. This is going to be the same for every instruction because we don't know what instruction we're fetching until after we've fetched it. So let's think about what we need to do in the context of this picture. Well, we need to send the PC into the memory address. And we can see that we have a MUX here because sometimes we're writing data or loading data for load and store instructions. So we need to set this MUX here, MUX address to 0 to take the top address. We need to make sure that we're enabling memory operations. So we'll set this high. Read and write should be set to 0 so that we're reading. And then we need to be able to write into this instruction register. Again, the instruction register is remembering what instruction we're executing, because since this is going to take multiple cycles, we're going to have to remember what we've loaded from memory. So those are the things that we need to set here. And then we also need to calculate PC plus 1 at some point. We could think about, oh, since this is multiple cycles, could we do this later? We'll see. It's going to be a bit cleaner if we do this now because nobody else is using the ALU right now. So we'll also send the PC here all the way down to the ALU. We'll have to make sure that this MUX is reading the top inputs. We'll set the ALU to add numbers along with the value 1. So that's this mux here is going to have to be set to 1, 0 to read that second input. And we set the ALU to add the numbers. But we're not updating the PC yet because this ALU result is going to get stored in a temporary register, and then we'll update it the next cycle. So we're not updating the PC. We're not updating the register file yet. We're not writing anything. So all these other muxes we can set to whatever. It doesn't matter. Any questions on why I need to set any of these values to be whatever I've set them here? And again, as a reminder, X just means you could set it to a 1 or a 0, whatever's easiest. It's going to work either way. Is mux ALU 2, J, and K, Howard asks. So J is mux ALU, oh, sorry. So yeah, mux ALU 1 and ALU 2 are these two muxes here. So that's I and J right here. These are those two muxes. K is the ALU operation. I, comma J, PC is A. Any other questions on this slide?
What is that control red circle there again?
The control, oh, so this this control blob here, this is basically the control ROM that I had down here, but I changed the notation a little bit just because it's going to be cumbersome to have that giant block down here and controlling the wire. So control is just the control ROM, and it's anytime I have red signals, those are somehow getting connected from the control ROM. Again, I'm making a lot of simplifications here just so we don't have wires going all over the circuit, which is actually what would be happening in a real circuit. You got all these multiple dimensions of wires running around. I'll try and use color coding to make that a little easier to read through.
So A, B, C, and D, for example, and all the other ones are all connected to control and not just E?
Correct. All of the signals here are coming from E, and actually E is supposed to be going behind this control and going into the instruction register. So that's the E signal there.
Okay.
Again, it might be better to put this somewhere else. I'll think about other ways to make this clear in the future. But yeah, is that clear for everyone exactly what these signals are being laid out? Yeah, so some of these, even though I've only drawn one line, like here, this mux, this is going to be a 2 input signal because there's 4 inputs. Yep, J is 2 bits. I think the rest of these are single bits. At least the red signals are signal bits. Okay, so that's the fetch instruction. Here's the signals for all of those. And then we can build the control ROM again. Anywhere that I'm supposed to be outputting a 1, I'll just put a dot on that ROM to signify that I'm making a connection between the row and the column to drive a high voltage. So here I only have 3 1s, the 3rd bit, 5th bit, and the 2nd to. So on my ROM diagram, my 3rd bit, 5th bit, and 2nd to last bit all get set high. Those are the output signals. And then for each state, I also need to figure out what is the next state. So I was representing this state diagram where fetch was the 0 state. And then we always go to decode after that. That's the next state, which is state 1. So I'll do the binary encoding for 1 is just 0, 0, 0, 1. So the next state, when I read out the fetch control information, will be 1, which corresponds to the decode state. Again, I think a lot of people get tripped up on this diagram. This would be a good point to ask any clarifications on what exactly I'm doing here with this 2-dimensional ROM and placing dots to represent driving a 1. I'm just going to take these red signals. These red signals are the red signals that we saw on the previous slide going into the muxes and the enables and ALU operation. What does each row of wires represents? So this is the opcode coming in here. Oh no, it's not the opcode, sorry. This is going to be the state, which is initialized to 0, and then this corresponds to each state in this, actually it's probably the next one, yeah. Each state of this diagram corresponds to a row in that ROM. So the first one corresponds to row 0, which is the fetch cycle. The second one corresponds to state 1, which is the decode. Each of these states corresponds to a row that we're driving the output logic and the next state logic. The same way that when we had our finite state machine for the vending machine, each state had its own row in that. That was at least combination of state and input, but same basic idea. Would it be accurate to say each row is also a cycle? Yeah, so each row, we're going to be in one row for a given cycle, and then we're going to jump to a next row the next cycle and just kind of keep popping around. Okay, so now let's think about how decode is going to work. So in order for the decode stage, what we're defining the decode stage to be, and this is somewhat arbitrary, the way that I'm slicing up these time cycles. We could have done more stuff in one cycle or break something up into multiple more cycles. This is fairly representative of how early processors worked, but this isn't hard, written in stone exactly how you're supposed to break up these cycles. We're just kind of saying, here's what we're going to do for this implementation. So what we're saying for this cycle in the decode stage, we're going to read the results of the instruction register, which is holding the instruction we grabbed from memory the previous cycle. We're going to take the opcodes of that and send that to the control logic, which is also keeping track of which state we're in. And then we're also going to read out the register, or we're going to send the values of what we need to read from the register into the register file in this cycle. We're not actually going to get the results until the next cycle. So we're breaking up the register file into more than one cycle just to read stuff out. But we're sending in the indices now so that at the start of the next file, we're sending the data out. And then also because we stored PC +1 on the previous cycle, and since we're probably going to be using the ALU on the next cycle once I get my data, I'm going to go ahead and take the result that I saved in this register, the ALU result, and send that back and store it into the PC now. And I'm just going to keep that PC at that value until we're actually fetching the next instruction. Norman asked, in the fetch cycle, the instruction opcode is fetched? Yes. And the PC is incremented? Not quite. We have an incremented value of the PC, and that's getting stored in the ALU result. It's not until the decode stage that we're actually taking that value and writing it into the PC, effectively incrementing it by 1. Again, there's no inherent reason that we couldn't have done that on the last cycle, but maybe it's the case that when we tried to design that, the clock period was too long to do both of those operations in one. So we're just splitting it up into 2 operations here. So in order for this to work, I'm updating the PC, so I need to enable the PC to update. I am not updating the instruction register because I already loaded the instruction last cycle. So I want to hold on to that. And the way that I hold on to it is to disable it. I'm not reading anything from memory, so I'll go ahead and disable that. I'm not reading anything from memory at this cycle, but I will do it. Sorry. I am reading something from memory this cycle, and the data will be available, but I'm not writing anything to memory. So this is really a write enable right here. And I'm not writing anything, so I'll set that to 0. And then I'm not using the ALU at all. So all of the MUX MUX inputs and the ALU operation, we can set everything else here to X's because it doesn't matter. We're not using that hardware right now. Any question on how we're implementing the decode stage? We're decoding the instruction that came into the instruction register by reading it into the control and also looking at specific bits to figure out which registers do I need.
So we're not actually reading the registers.
Basically, what's happening inside the register is that we're sending in the register indices, and the register file is reading the values, but it's not outputting them yet. It's basically just getting it right, right up to the gate, and it's getting ready to go, so that immediately on the next cycle it can dart out of the starting gates and go into the ALU. So we're not wasting time on the next cycle waiting for the data bits to go through. It's not super critical that you are thinking about it that way, but just know that immediately at the next cycle, the data here is going to be getting output. How is the net state being determined by this cycle? Very good. I'm going to defer that question just a moment, Norman. But yes, you're right to be a little concerned about how we're going to calculate the next state from this. But let's go ahead and figure out the control signals first. So again, most of these are nice because we have a relatively few things being set 1 for each instruction. So we have a 1 for the 0th bit, and that's it. That's the only 1 we have. So when we're designing our control ROM, we can set a 1 here and leave everything else 0. But I have question marks right here for the next states because as Norman was indicating, if we look at the control diagram here, most of these state transitions are pretty easy because there's just one arrow going somewhere else. This add cycle is going to go here. Fetch always goes to decode. This one, we have a bunch of out arrows going. Why do I have a bunch of out arrows going? What is going to determine which of these arrows I take?
The instruction.
Yeah, specifically the opcode that I fetched in the previous cycle. So I'm not purely just going to be able to look at the current state. I'm going to have to look at, okay, I'm in the decode state, and then I have to look at the opcode. So it's not too complicated how we're going to end up implementing that, but for right now, I'm just going to focus on the simpler cases. So let's just leave these as question marks, and we'll figure out how to do this in a few slides. But any questions for how we set the control ROM for the decode stage, ignoring the next state logic? Anthony asks, is reading from register always assumed? Because for memory, there's an enable read write, but for register, there's only enable write. Yeah, we'll assume for this that our register is always reading values out. No inherent reason why we had to do that. Registers generally are, a lot smaller than memory, so we're not wasting nearly as much energy as we would be if we were like always activating memory. So it kind of has to do with the details of how they're implemented in hardware. But yeah, for now, you can just assume registers always read. Memory, you can just switch off the entire read-write circuit if you want to, though. Okay, let's jump into the first add cycle. So again, we didn't really talk about how we would know that we would go to the state, but we'll come back to that. Let's assume that now we are in the add cycle, the first of 2 add cycles. Okay, so here's the data path. Let's think about the current state we're in is we already sent the addresses into the register file. So now the register file has latched onto those addresses, those indices, and it's just going to be outputting the data for the entire cycle. So we have the values coming out here. We obviously need to set these 2 muxes to be the appropriate value. The top mux, we're taking the bottom value, so that should be set to a 1. This bottom mux, we're taking the top value, so that should be set to 0. We're not updating the register file or memory or the PC, so these all get set to 0 or the instruction register. And then again, everything else we can set to X, don't care. Any questions on these control signals? Okay, so again, we only have one thing that needs to be set to 1, and that's the 4th from the end. So here I'll set this as 4th from the end. And the next state logic here is easy. We were in state 2. The next state is always going to be 3. So we'll just encode a binary 3 for the next state. Quick informal participants poll. If you click on the participants tab, just do a yes if you're following along, no if this isn't clicking. One hand clap. Okay, so it's about 2/3 are following along. Those not following, ask questions now. This is the time to figure it out, because if you're not getting it now, you're going to be lost the rest of the lecture, and it's not going to be a great use of any of our time. Any questions I can answer? Norman asks, is ALU result always reflecting the result of what is being input into the ALU? Yep, so if it's a 0 that we're inputting into the ALU control, so the ALU op, if this is a 0, then ALU result is always storing the sum. If ALU op is 1, then it's always storing the NOR operation. But we're not always going to use the result of ALU result, because this is going into the register file, it's going into the memory. So if we set these muxes or the enable switches accordingly, then we're basically just ignoring that result. Yeah, so the next state result, so this is going to be outputting the binary encoding of what the next state should be. And so we're just going to have 4 flip-flops here that is holding on to what the current state is. So this one goes here, this one goes here, this one goes here, this one goes here. So every clock tick, we're remembering what the current state should be, and then we're just looping this back up into here. Except actually do the right ordering of that. Yeah, so Hallie, the reason why we have question marks here is because going from the decode state into the next states is more complicated than all the other ones. Every other state besides decode has exactly one output arrow. So we always know what the next state is going to be. But the decode stage, it depends on more than just the current state. It depends on what instruction we fetch to figure out, are we supposed to be going to the add cycle or cycle load word? So right now I'm just putting those as question marks. We'll figure out how to do that in a few slides. I'm just kind of ignoring it for now so we can focus. Why do we input 2 zeros into this mux? So this mux has 2 zeros. So are you asking why we have 2 inputs, or why specifically it's 2 zeros? The reason why we have 2 inputs is because there's 4 possible inputs. So it would take log 2 of 4, which is 2 bits to identify which of these 4 things we're actually wanting to pass through. The reason why in the add cycle we're specifically doing 2 zeros is because we're taking the top input, which corresponds to register B. Yep. And then question marks, again, we're going to talk about the question marks later. Just ignore those for now. Okay, and I think, again, the more examples we go through, the more we can kind of compare across different ones, and hopefully it'll make more sense. So let's do the next cycle of the add. So the state of things after the previous cycle was we were computing the addition, and we stored the result into the ALU result register. So now the only thing left for the add instruction is to send this result back and write it into the register file. So we need to make sure that we have the index for the register that we're writing that's still being saved by the instruction register. So we'll look at a few specific bits there and send that into the write index. The data is coming from the ALU result. So we need to set this mux to 1 to grab the bottom one. This one's going to be 1 to grab the bottom one. And we have to enable the register file to be able to write. So that top mux is 1, this bottom mux is 1, the enable switch is 1. We are still not modifying memory or the PC. So those, or the instruction register. So all of these enable switches get set to 0. And then everything else doesn't matter. So we'll just set these to X's. This one's a bit simpler. We're only updating the register file. So we're just kind of narrowing our focus to a very small part here. Any questions on this one? We do have more ones in this case than some of the other ones. So we'll just have to make sure that those ones get set appropriately here. And then the next state logic, we're just going back to the fetch stage in this case, right? We're looping back and going to state 0. So we'll just have none of these bits set to say the next state should be 0. Any way to zoom out? Oh yeah, if it's blocking by your zoom. Unfortunately, I don't think I can zoom out any further. Depending on your, yeah, I don't think the desktop app allows you to move the zoom bar, unfortunately. But I'll keep that in mind for future lectures. Maybe I'll try and avoid having anything below in the lower portion. Are these suggestions about the window for
Yeah, if you go into view options and click side by side, it'll bring you to a smaller area. Then you can click it to fit the screen. It's not optimal, but it still fixes the issue.
this is view options on Zoom or PowerPoint?
In Zoom, there's a side by side mode at the very bottom, and then at the top, there's a zoom ratio.
Side by side. Not seeing this option. Well, I'll take a look at this later and see if I can't fix it for later instructions, or later sessions. But I want to make sure I can get through the material today. So I'll try and explain anything. If anything's blocked off, let me know, and I'll try and explain it better. Okay, so let's look at, so we do the fetch cycle again, and we do the exact same thing now. It doesn't matter what instructions we did before. We've already figured out how to do the fetch cycle, so that's all we need there. So let's just think about NOR. How would NOR be different? Yeah, let's think about that. So that's going to correspond to this state here. My question for you all is, how many control bits are going to be different between the first state of NOR and the first state of add? So specifically, state 2 was this one here. This is when we were doing the first cycle of add. How many of these control and next state bits are going to be different? Open up this poll. Anthony asking, why is the second state of add different from the first? Well, if the second state of add was exactly the same as the first state of first, then they would be exactly the same state. In which case, why would we have two different states? It's implying that we're doing two different things across two different states. Otherwise, we just merge it into one. Specifically, the first state of add is adding the numbers and storing the result into that intermediate ALU result register. And then on the second add state, we're writing the result back into the register file. So that's different control signals because we're using different hardware across those two states. And then the next state logic is also going to be the same. Let's take 10 more seconds. Close the poll in 3, 2, 1. Okay. Most people saying 1, and I think that's pretty common for people to say, but that is not correct. So the obvious one that we're changing. So yeah, somebody tell me what's one of the signals that we're changing between the second state of add, or sorry, the first state of add and the first state of NOR. What's the obvious one? Yep, the ALU operation. We're doing a NOR operation instead of an add. That's going to have to be a 1 in this case since we're doing the NOR operation. But there's one other thing that we have to change that. Oh, you know what? The way I worded this. Sorry, my bad. You're all right. So the control bits, yeah, there's going to exactly be one difference here. In addition to the control bits, we also have the next state bits have to be different. But yeah, I did not word it that way. So you're all good. The next state bits are also going to have to be different. And if we see here, we're in state 3, we're going to state 4. So we'll set this to be well, that doesn't seem right. We're in state, oh, sorry. Yeah, this is state 4. We're going to state 5. So yeah, we're in state 4. So the binary encoding of that is going to have to be 5, which is 4 plus 1. So we put 1 and 0, this 4 and 1 bit set high. And then if we looked at the next state is going to be exactly the same as the second stage of add, where we're just taking the result and storing it into the register at the end, and then we're just going to the fetch stage. So technically, we could have actually merged these two states into one. That's what it means when the control ROM is exactly the same for both of them. We could have just said, hey, both of these are going into the ALU write back stage, and then just have this one go there. You know, we could have saved an extra row in the decoder, but it doesn't really matter because we need a power of 2 anyway. So it's probably easier to understand if we just have these be 2 explicitly separate states, even though they're doing literally the exact same thing. Yep, states 3 and 5 doing the same thing, just taking the ALU result, writing it back into the register file, and then we go back to the fetch cycle. Okay. So this is what everything. So the transition function circuit is going to look like this, except for we haven't figured out these 1 bits here. So I mean, we haven't gone through load and store yet, but it's the same basic process. If you've been following along, you should be able to figure out how to fill in the rest of this. But yeah, the one weird thing is that when we do the decode stage, the state that we go to doesn't just depend on the current state, but also the opcode that we fetched. So we're going to add a little bit more circuitry here. If we know what the opcode is and we know that we're in the decode stage, then we know completely what the next state is. So we can use a separate, smaller decoder that takes in the opcode as the input to the decoder, and then we're just encoding the next state for each particular opcode. So the first state for the add instruction is 2. So I'll do the binary encoding there. The first stage of the NOR operation is 4, so we'll do that. Load word is 6, encode that. Store word is 9, encode that. And then we just need to figure out whether we're supposed to use this next state logic or this next state logic. So one trick that I'm just going to do is say, hey, let's put all these question marks. Let's just set these all equal to 1. And we can do that because we didn't use all the possible states that we could. We only have 13 states. So this is basically corresponding to the 16th state. And so we can just set this all equal to 1. That way, if we ever read out 1, 1, 1, 1, 1 for the next state, well, we know that that can't be a actual next state because there is no state 1, 1, 1, 1. So instead, we're just going to feed all of those into an AND gate. and have that be the driving force for this mux, where we say that if this is all ones, then we should use this second decoder that's telling me, okay, this is a decode instruction. I need to look at the opcode to figure out the next state. Otherwise, if not all these are ones, then this must be a valid next state, and we'll just take in whatever that's telling us. So right now, the only scenario where we're using the next state is where all these bits are 1, because we just hard-coded this to say spit out all ones when it's in the decode state. Any questions on that? It's kind of a little trick hack thing to make this a little simpler. And then, yep, whatever the next state is. Well, so first it's going to get stored into 4 flip-flops so that we remember the current state. And then we send this back to the decoder. So this is next state on the left of the flip-flops, and then state on the right of the flip-flops. Howard asked, does decode take 2 cycles or no, because it's combinational? You're exactly right, Howard. This is all combinational logic. All of this is combinational logic. So this is going to take 1 cycle for the state bits to go into the decoder, spit out the next state. We'll send this into a mux and choose either between this decoder or this decoder, making the next state available for the state registers on the next edge of the clock. Is the state register shown in the circuit? Not explicitly. That's going to be part of the control logic here. This is going to have some registers that are keeping track of what the current state is, where control is basically a finite state machine. So we're abstracting all the complexity of the ROMs and the state inside of that control block. Good question. Okay, so we'll replace these question marks with all ones. We know that all ones doesn't correspond to a valid state, so we'll know to interpret that as look at the opcode decoder to tell us what the next state is. Okay, let's just go through some of these other ones. So load word is going to be a bit different than the other ones. We've already read the registers on the previous cycle. That's what the decode stage was doing. But now we need to read the contents of register 1 and add that not with the contents of register B, but with a sign extended offset. That sign extended offset comes from the instruction register that's holding the instruction. We're setting those into the mux and into the ALU where we'll add them together. So this top mux is using the bottom input, that's a 1. This mux is going to be set to 1, 1, since that's the third input. The ALU, we're adding stuff together, so that's going to be a 0. And we're not updating the register file or the memory or the instruction register or PC at this point. So those are all 0. And then all the other muxes, we don't care. The only thing that's really different about this one is this mux here, we're grabbing a different parameter than what we were doing with add. And so this is what that load word cycle is. And as we can see, the only difference between this one and the add cycle are these 2 bits here. Otherwise, it's the same. And obviously, the next state logic has to be different. Questions on load word? Okay, and then on the next cycle of load, load words are kind of the tricky one, right? Because we're not writing into the register file. First, we have to read from memory, and then we'll write it into the register file. So we're taking this U result back not to the register file, but to memory. So we're going to have to make sure that we set this mux here to be 1 to get that bottom input in. We are dealing with memory right now, so we will enable it. And then we're reading from it, loads read from memory. So we'll set read write to 0 to mean load. Not updating the register file yet, not updating the instruction register, not updating the PC. So all those are 0. And as always, all the other muxes we're not using, so we can just set those to whatever. So we only have 2 ones here. So we'll set the control Rom for those 2 bits to be 1, and then the next state is 5. So is it 5? How did we encode that? Got to have these flow diagrams more evenly spaced. Okay, so this is cycle 7. So then the next cycle is 8. Okay, yeah, the cycle number doesn't correspond to the state number. So this is 7 here to go to that state. And then here we're going to state 8. So we set the 8-bit high there. I get nervous when there are no questions because I'm worried people are just completely lost at this point. Let's do another quick participation poll, or participants poll. So I'll clear it. Yes, you're following along. No, this is not making sense. Okay, so it sounds like most people are following along. So maybe we've just gotten far enough that it's clicking and you don't have questions. For those of you that this is still not making sense, definitely take some time, work through these slides on your own. Come to office hours if it's still not making sense. If it's not clicking in this format, if we just have a one-on-one conversation, it's really not that complicated. You just kind of have to have it explained in whatever way kind of resonates for you. It's hard to do it when we have 100 people here. And we can't get that back and forth. So especially after the project is due, office hours are usually very light. Come by, we'll walk through these slides. But you want to make sure that you understand this stuff before we get to the later projects and the exam. Exams are often going to cover single cycle, multi-cycle stuff. So Jack is asking how we can set stuff to X without throwing things off. So X, again, means we can either set it to a 1 or we can set it to a 0. I'm just setting all the X's to 0 here because, extra dots on here is confusing. So zeros, I think, are less clutter. But the reason why it doesn't matter is because, like in this case, I'm not using the ALU at all. Or actually, let's do a simpler example. The register file is not enabled. So whatever data we're writing to, quote unquote, writing to, whatever index we have here that we're writing to, it's not going to have any difference, right? Because this is not enabled, so we're not going to update the state of the register file. So that means that when we're setting these muxes here, whether it's a 1, whether it's a 0, it doesn't matter. We're just sending different data that's going to get ignored anyways. Some of these are a little bit more subtle for why it doesn't matter. Like we might think, okay, why do these not matter? Because aren't we storing the result in the ALU result? And that's true, we are storing that result, but on the next cycle, we're going to encode this in such a way that that result is just going to get thrown away. So we know that the way we're designing this finite state machine, that some of these results are just going to get thrown away. So it doesn't matter whether it's a 1 or 0. We have to set it to one of them. There's no other option besides 1 and 0. But that's what we're doing here. Okay, and then the next cycle of the load word. So now, and so on the next cycle, memory is just going to have latched onto that address and be spitting out this data. So we need to send the data into the write data of the register file. We need to grab the destination register from the instruction register. So somebody remind me, with a load word instruction, which bits are we using? Are we using the least significant bits of LW, so 0 through 2, or are we using that register B for the target destination of register. Either over your mic or over chat, which one are we using, register B or register C? Yep, register B. That's the one weird instruction that just doesn't use the last target. So that's why we have this mux in the first place. We're choosing between those 2 bit fields. We're using the top one here. So we need to set that mux to 0. This mux is taking whatever we read from memory. So that's going to be set to 0. That's the data that we're writing. We're not updating the instruction register yet, or memory, or the PC. So those all, yeah, we are updating the register file we're writing this data in, so that's 1. But memory, the PC, those all get set to 0, as well the instruction register, and then everything else, we're not using that data. So again, we just set it to whatever, because we're throwing those results away. Norman had a question a little while ago. When we say read the memory location, what exactly does that mean? Load the address register in the memory. Yep, so we're sending in an address. So this is no different than what you were doing with project 1A, right? You're sending in the, we have an address. We're sending that address to memory. Memory is just a big table of values. We're looking up that address and grabbing that piece of data there. Do we still not need the register enabled for B? So the enable is for the current cycle. So on the previous load word cycle, here, we did have it enabled because that was the cycle that we were actually reading it. But on this cycle, we've already read it, and the memory is just latched onto that output. So the enable is for the current instruction about whether we should be currently grabbing something. Here, it's already been grabbed, and we don't want to grab something for the next cycle, so we're just setting this to 0. What is the 2 muxes in the middle again? So here, as I mentioned, sometimes the destination register, like if we're doing add or nor, it's the register C is the destination register. For load words, it's the register B. So that's why we have to have a mux here to choose which one is going to be the right index for this particular instruction. And then this one, the data could either be coming from memory, like a load word, or it could be coming from the ALU, like an add or nor operation. Okay, so this is what you get for the control ROM there. And again, this is the last cycle of load word, so we're going to go back to fetch after this, so all of these can be set to 0. Okay, store words. If you followed along with load words, store words should be pretty straightforward. We're doing the same thing. Only thing that's different for this is that we're not writing anything to the register afterwards. So the only difference between this store instruction and the previous load instruction, which was this one, is the next state, because the first state we're still adding together to get the offset. And then it's the next cycle that's a little bit different, because now we're writing to memory instead of reading from memory. So that bit's going to be different. But otherwise, if you were able to follow loads, stores are very much straightforward, except for that load read writes. And then we don't have that additional cycle at the end where we're reading into the memory. So that's going to be the same. Branches, little funkier. So remember that we already stored PC plus 1. And that got stored into PC. We immediately incremented PC on the fetch instruction. We stored the intermediate result. And then on the decode instruction, we took that result and stored it back into PC. So PC is already storing PC plus 1. And now I need to calculate PC plus 1 plus offset. So by the way, if you were curious about why does LC2K have PC plus 1 plus offset for branches versus ARM has PC plus offset, this is why. Because when we designed that architecture, we knew, hey, it's going to be slightly easier if we just do PC plus 1 plus offset, because the micro architecture would have already stored that value PC plus current PC. So if we were going to do PC plus offset, we would actually have to minus 1 at this stage. So we were thinking ahead, and we designed the ISA around the micro architecture. which is not always a great thing to do. Sometimes you get weird esoteric stuff, but sometimes you can get more efficient hardware that way. But anyways, this is storing PC plus 1. We're taking that value and we're going to add that to the offsets. The instructions are already stored in here from the decode stage. So we take the offset bits, sign, extend that, and send that into the ALU here. So we're calculating PC plus 1 plus offset. So we're going to set that top mux to 0, this mux to the bottom 1, 1, 1, and the ALU results, we're adding these together. So we set that to 0. The result is going to get stored in the ALU result register, not the PC on this cycle. So we're going to disable the PC enable. We're not doing anything with memory. We're not doing anything with the register. So all those get set to 0. Everything else gets set to X. This is what the control ROM looks for that. So the PC enable, so just like anything else, all the enables work exactly the same way, except for memory. Memory's a little different. But all these registers here, if enable is high, then we're taking the value that's in the left and we're storing that result. Here, PC, we don't want to increment this cycle because it's not going to be available to the next cycle. So we're disabling it. When you disable and enable for a register, you're saying, just remember your old value, don't change it. So this is the control ROM for BEQ with the next state. The next cycle of BEQ, we saw how we have to add some extra gates here. This is where we're actually reading out the 2 registers of the branch instruction, and we need to see if they're equal or not. And we saw how we modified the ALU to just have this extra bits that we don't need to enable or disable. It's always just going to be checking to see if these 2 things are equal to each other or not. So the top mux here needs to be 1. The bottom mux needs to be 0, 0. ALU doesn't matter because it's always going to be outputting that equal bit. But then we saw we have this extra control logic over here. This AND gate is checking to see if this is a branch instruction and if this equal output is true. So this is just magically going around and sticking into there. So if that's true, then we'll enable this PC. But remember that before we often had a hard-coded value going into this PC enable. I still want to be able to do that. I want to say if the decoder is outputting a 1, that we should ignore this logic. So we're just going to stick an OR gate here that allows the decoder to override this logic and say, no, ignore whether it's a branch instruction or not. I'm enabling the PC right now. So we'll just set that OR gate to 0, which basically makes this transparent. If this was a 1, then we would ignore this stuff. But if this is a branch instruction and the 2 register values are equal to one another, then we want to enable the PC so that we update and take the PC plus 1 plus offset, which is being stored in this ALU results that should write back and get stored into the PC at that point. Any questions on branch instruction? Why is a 0 in the OR gate again? So do you agree that if we have anything ORed with 0, that it just becomes whatever that first thing was? If this is true, the output's going to be true. If that's false, the output's going to be false. So here we're just ignoring the second output here because it's a 0. But if this was a 1, then we would basically be saying, anything ORed with 1 is going to be true, regardless of what X is. So this just gives the decoder a way to say, hey, for all of these other slides that we had in the past, like here, I said 0, sometimes I said 1. This gives us a way to short circuit and say, ignore the branch. Basically, this gives me a way that I don't have to go back and modify all my slides. I can just pretend, oh yeah, we also have this little extra circuit here that's detecting if this is a branch. Yeah, not too critical as long as you're understanding the basic principle of how this is working. So it can be a 0 or 0 equals 0 during the BEQ cycles. Yep. So if you have 0 or 0 because the equal is false, then we shouldn't update PC because PC already has PC plus 1 from the decode cycle. Cool. Yep. So this is a very dense lecture. I think a lot of it is just stuff that you kind of want to go through on your own at your own pace. Make sure you're understanding it. Definitely come to office hours if this just isn't clicking. Again, I don't think it's too complicated, but if you're lost at the beginning, it's you're probably lost for most of it. So I think it can be really helpful just to talk with someone who knows this and kind of walk you through it in more detail, where you can ask questions and not worry about the 65 other people here. So we'll break for today. I'll just mention that we're not going to worry about jailer instructions pretty much for the rest of class. We need to have a jailer instruction in order to do function calls, but it's just so tedious to have to figure out how to implement it. If you understand all the other instructions, it's the same principle, but it just adds a bunch of gross circuitry that's hard to draw down. So we're not going to worry about jailer instructions. We will pick up here tomorrow and talk about how this improves over single cycle, whether it does improve over multi-cycle, and where we go from here, because hint, we're still going to find improvements and we'll figure out how to make better processors going forward. But we will pick that up not on Monday, right? Because Monday's a holiday, whoop, whoop. But we'll pick up on Tuesday. And yep, good luck with the project. Don't rest too much on that extra day. Get it done as soon as you can so you can get started on the remaining projects. Okay. Thanks, everyone. We'll break there. I'll answer questions for the next 15 minutes.
Hey, John. Oh, sorry.
Yeah, go ahead, Alex.
Okay.
So if you go back one slide.
Yep. This one.
Slides, I think. One more. To like this one, yeah. I think I might have missed this. The ALU result here is storing PC plus 1 plus offset, right?
Yes, if this is equal, then we're storing the result of ALU result, which we calculated previously to be PC.
Yeah,
plus
previously,
yeah.
because I was gonna say, what was I gonna say? Oh yeah, in this case, why is the ALU not storing the result of the sum of the two muxes into ALU result and overriding it?
So it is actually. So because this is, it's either a 0 or a 1 here. So it's either adding or ignoring it. On the next cycle, we are going to write that result to ALU result, but that's not going to update ALU result until the next clock tick. And until that point, ALU result is still outputting that result. And then on the next clock tick, the same time that we're overwriting this value with the garbage ALU result, we're also updating PC plus with the correct value at the same time. So we're saving it as soon as we're erasing it. So the value is still there. Oh,
I see. Because that's a register. So
exactly.
Oh yeah, there's a little black line in between. Okay, that makes sense. Okay, that answers the question. Thank you.
Do you have a question, Rena?
Yeah, I just had a really quick question that isn't directly related to like the material, but do you think it would be possible for you to hold individual office hours like today or tomorrow?
Yeah, I'll try. I'll definitely hold some tomorrow. At least I'll try and see if I can hold some later today. But I have to figure out some meeting schedules first. Yeah, I'll definitely hold some tomorrow.
All right, thank you.
Wait, but there already is individual office hours at 1 p.m., right?
Yeah, but
1 p.m. Pacific, sorry.
But yeah, if you want to specifically talk with me, I'll hold some office hours later.
Okay, yeah, thank you.
Absolutely. And I guess, so for those of you who are still here, so I'm trying to figure out what the screen issue people are talking about, because I have a second Zoom instance that I think is just showing what you're all seeing. And so I do have like a toolbar at the bottom, but I'm still able to see the full screen that's on my other tablet. So for some of you, are you like seeing these values cut off?
So yeah, the issue that I was having was if you have it in order to only see your window as opposed to seeing like other participants, which like I guess isn't super, distracting because everyone's like video is off, but I had it in full screen so I could see like you in the top right sort of, and then the slide.
Okay.
But the problem with that is that the bar at the bottom that has the chat participants, all those sort of options, was covering that last part of the slide. So you just can't really have both, which is fine.
Gotcha. So that was something that you changed on your end to be able to see. screen. Okay, yeah. So yeah, I don't think there's anything I
remember
can.
it being like that yesterday.
Uh-huh. Okay. Yeah, I'll try and keep that in mind. Maybe I can add a little bit more buffer room in these slides so that if people do have that set up, that it's not cutting things off. But I'm just inheriting these slides from previous semester, and it's a bit tedious to make changes. So might be feasible to do it for some of them. But yeah, that'd be good if we had like a procedure. So if people have that issue in the future, we can just say what to do. So you're saying that
It was
in order
super
to fix
simple.
that,
It's just
Yep.
it was just like don't have the thing in full screen, basically.
okay,
was-
don't
was
have
the
the Zoom
solution.
window in full screen.
Yeah.
Okay, good to know.
I guess I had a question about the first. I can't remember what they're called, but not the specific opcode instructions, like the first two, the decoder and
the fetch and the
the
decode.
fetch. Yeah, those ones I think it was because I hadn't seen very many yet, but I was pretty much completely lost at that point.
Okay, yeah, I can hop back to those. Let me just see in the chat if there's stuff about these couple slides so that I can handle those while I'm here at least. Okay, so Allison asked, how is the ALU register not being overridden when register A and register B? So yeah, I think I answered that now. So it is being overwritten, but at the same time that we're overwriting it, we're taking the good result and storing it into PC. So as long as we're moving the values forward, and it's good to get this because the next processor type we're going to talk about has just a bunch of these registers all in a row, and we're continuously passing them one to the next. This is called pipelining. And you're going to be overwriting the values but saving them in the next register at the same time. So it's good that you're thinking about this now, because it's much better to resolve that uncertainty here to when we all of a sudden have like 5 of these registers overwriting each other at the same time. But does that make sense, Allison? All right, I'll assume it makes sense. Mohammed asks, what is op again, and for the gate again? Oh yeah, so the op, this is the op code. So the same bits that are going into the control register to figure out what we're doing. Those opcode are going to go in here, and this is just checking if it's 100, which I'm assuming I did this correctly, and this is the branch instruction. So if this is true and they're equal, then we need to update PC to PC plus 1 plus offset. Okay, cool. And Norman shared a screen cap of how to do that. Thanks for sharing that, Norman. So I can hold on to that and share that with people if they have that problem in the future. So Eleanor, I'm having a hard time remembering what all the muxes are doing. Yeah, so totally understandable. There's tons of crap going on right here. Honestly, like when I'm going through this, I don't like immediately remember like, oh, why do I have this top signal into the mux? Really, I just worry about on a case-by-case basis, what input do I care about? I don't necessarily care about where the other ones are used on occasion. But if you understand each instruction in isolation, then you can just kind of take it on faith that like, okay, I did understand these other instructions when I was handling those. So, you know, somewhere we were using these bits. And that's really important to be able to kind of abstract your mind and compartmentalize these things, because this is a really simple ISA, relatively speaking. Most ISAs, right, there's just so many instructions. And if you were actually working on the hardware, right, like nobody remembers like every single mux input. You know, you just ask them on a dime, hey, what's this one for? They'd be like, I don't know. We figured at one point we needed it, so we put it there and we tested it and it was good. So I'm just trusting that it's there for something. All I know for right now is that the BEQ instruction needs, you know, register A. So that corresponds to these bits. I'm not going to worry about what these other ones are doing. That being said, the more you kind of work through these problems, and especially once you're working with the later projects, when you're actually building a simulator for these things, you'll start to get more comfortable with it. You'll remember it more easily. But more just focus on understanding for a given instruction, which signals do I need, don't worry too much about why the other muxes are there or what the other signals are doing. But let me see if I can dive a little bit deeper into your question and resolve anything. So going left to right, it seems like, so PC, so yep, okay, so yeah, you're just looking at these. So yep, this is the PC, because sometimes we're using the PC to access memory when we're loading an instruction, and sometimes we're using the ALU result, which is the load and store address plus offset. That's going into that mux. This mux here, so yeah, this top one here is this is the destination register index. And the reason why we have two inputs to there is because the ISA for LC2K, there's two different spots that can indicate which one is the destination register. For ANDs and NORs, it's the last register, bits 0 through 2. And then load word is the weird one that has register B as the target register. So this bottom one is for ANDs and NORs. This top one is for load words there. And then this mux, this is the data that we're writing. And if it's a if it's a load instruction, that data is coming from memory. So that's what this top input is for. The bottom one is if we're writing something, again, from an AND or NOR instruction. So that's coming from the ALU result. And then these two muxes are determining what's going into the ALU. So we might be doing PC plus 1 or PC plus 1 plus offset. So that's why we have this result coming down. This is just if we're adding or ignoring register B with something. This is if, that's register A. For this mux, we're choosing the second operand. This one is if it's register B. This is if we're doing PC plus 1. 0, we didn't really talk about, but we can get to that later. And then the bottom one is if we're adding something with the offset, which is what would happen with load or store words, because we're adding a register value to an offset. So yeah, that's a quick primer on the muxes. But again, just make sure that for any given instruction, you understand what signals you need. Don't worry too much about, I mean, it's a good exercise to get to the point where you can just kind of look at it and say, oh yeah, this is here for this particular instruction. But for right now, just focus on compartmentalizing for each instruction, knowing how that's supposed to work.
Hey, John, I have with someone else.
Yeah, go ahead, Jack.
Another question. I just have a high level question about some project stuff.
Okay, let me see if I can get through lecture related stuff first, and then yeah, I can take project stuff. Okay, so Ziran asks, can I explain why the shorter clock would help? So yeah, at first it might seem like, I'm just doing, snake oil salesmanship here, because immediately when you say, oh, shorter clock period, immediately that might seem good because it's like, oh, I'm doing more work in a shorter amount of time. And that's better. Higher frequencies are good, right? But then we might say, well, wait. If it's a shorter clock period, but we're doing less work overall in each clock period, doesn't that just cancel each other out? Like in particular, the load word instruction is not going to be any faster in this case. It's still going to take the exact same amount of time as before. It's just we're spreading that work across multiple clock cycles. And in fact, it's probably going to take a little bit longer because we're adding in, registers in the middle, and that adds delay with the setup and hold times and blah, blah, blah. What this benefits us for, recall that if I had an add instruction that takes, I forget what we said, like 4 nanoseconds or something. We had to do the register read and writes, that's 2, 4 for the ALU, 6 for the load. So we said that the add instruction took 6 nanoseconds before. This whole process took 6 nanoseconds. The problem was, because we were doing a single cycle architecture, even though we could do an add instruction in 6 nanoseconds, we can only pick one clock cycle. I can't just get 6 nanoseconds into my 8 or 10 nanosecond clock cycle and say, oh, I'm done. Let's just start the next instruction early. no, we can't update the memory until the next clock tick. So we just end up sitting around for several nanoseconds, even though we finished early. We're not benefiting from the fact that this was a shorter instruction. And because the load word instruction, I think we said, takes 9 nanoseconds, that was the worst case scenario. So we had to set the clock period to 9 nanoseconds. So the benefit of doing shorter clock periods and doing more clock cycles is that if each of these is, let's say 2 nanoseconds, so this one takes 3 cycles, and the load word takes 5 cycles. This is great because if we finish the add instruction earlier, we still have to wait to the next clock cycle before we can update anything. But because the clock cycles are happening more frequently, we have more granularity, where instead of waiting the extra 2 cycles after this add instruction, I can say, go ahead and fetch the next instruction. We can start it now because I finished early. So it really is just the granularity of when we can start and finish instructions. That's the benefit of having a shorter clock period. And if we're doing a bunch of adds, we can keep ending multiple cycles early. If we're doing single cycle, we can't end partway through a clock cycle. Cool. So Norman asks about the left mux that goes into the register. This one here, is this what you're asking about, Norman? Okay, so yep, so this is the right register index, right index. And the reason why we have a mux here is because there's 2 different types of instructions, add and nor. We have R1, R2, R3. This is the destination register for those, so that's what we want to feed in for the index. Versus load word, I have R1, R2, and -2, or not, yeah. And then in this case, this is the destination register for those. So because we're using 2 different bit fields in order to determine what the address is for different instructions, we need to have a mux with both of these inputs going in there. Okay, and then somebody was asking about the earlier Control Rom. I'll just quickly go through the first example again. And then I'll go on to non-lecture questions that people were asking about. Okay, so the first thing we do is the where was that slide? This one. Okay, so this is the first cycle we're doing. And now that we understand this data path a little better, hopefully this makes a bit more sense. So the first thing we have to do when we're fetching an instruction is I have a PC, starts off as 0, and then we're incrementing it later on as we come back. We need to send that PC into the memory address field. Memory will return that data on the next cycle, but all we're doing right now is sending that PC into here. And then we also want to send the PC into the ALU so that we can add 1 to it. And then on the next cycle, have PC plus 1. So in order to get this to work, we're not updating the PC right now, so that's not going to be enabled. But we are using memory, so that gets enabled, memory gets enabled. We're not using the register file, so that's not enabled. We need to select the top input from this mux. So the top mux is going to be 0, 0, or just 0 because it's a single select input. The bottom mux we're using 1, the hard-coded 1 value. So we'll do 0, 1 for that mux input. The ALU, we're adding stuff together, so that's 0. And then everything else is not getting updated. So all the enable registers are 0, and then all of the muxes that we're not using get set to X. And then when we do the decode instruction, so this is the state of everything after the fetch instruction. When we do the decode, now we have PC plus 1 stored here. So we're going to write that back into the PC, which means we're going to have to enable that to make sure that that change happens. We're not doing anything with memory because we already loaded it, and that's getting stored into the instruction register. So we don't need to enable this. It was already stored into the instruction register, so we don't need to change that. The register file, we're not... Sorry, I always get tripped up on this. We are reading from the register file, but we're not writing to the register file. This is a write enable. So we set that to 0, and all the other muxes don't matter. So whoever asked about this, does this make more sense now that we've kind of covered the later stuff? Any specific questions here? Norman asks, I wonder how we mask and extract the values of reg A, reg B from the instruction register. So we're not masking it. So this is the nice thing about hardware, Norman, as opposed to software. When we're doing software, we have to deal with, like if I have an integer, the integer has to be 32 bits, right? Or 64 bits or whatever architecture we're dealing with. So if I only want to look at specific bits in software, because this is like an atomic unit that I can't break apart, I have to do masking operations. With hardware, we can build whatever hardware we want. So if I want to just look at 3 bits, I literally just pull those 3 wires and put those into logic gates. I don't have to mask out the other bits. I literally just don't have hardware that's looking at those bits. We have much more flexibility in hardware. We can have any number of wires going anywhere that we want. Okay, Eleanor had a question on the homework. I'll hop over to that one, and then yeah, if people have project questions, we can take a look at that. Okay. Is this the problem you were looking at, Eleanor? Cool. So yeah, we're building a circuit. 5 bits of input, x3 through 0 and s, 5 bits of output. Both are 2's complements numbers. If s equals 1, then y should be equal to 2 times x. If s equals 0, then y should be equal to x divided by 2. In addition to wires, you only have 4 bits, 2 to 1 muxes to implement this. You may not add any gates. So yeah, at first glance, it seems like, well, how the heck are you going to do complex logic like this only using muxes? And we can take advantage of a few things. One is that if we replace this with arbitrary arithmetic, it would definitely be very difficult to do. But there's something pretty special about 2 times x. Anyone have an idea of why 2 times x is actually pretty easy to do? Yeah, exactly, Eleanor. All we have to do is shift it left, and that's going to be multiplying it by 2. And again, like I was mentioning to Norman's question with shifting, shifting in software requires an actual operation, an actual instruction. But if we're just dealing with wires, shifting is kind of trivial, right? You just move the, let me draw it out. So if I have something like this, if I have, these 4 wires, 0, 1, 0, 1, and I want to shift this up 1, so this is MSB, LSB, and I want to shift this up 1, I don't need any gates, right? I just say, this goes here, this goes here, this goes here, this goes here, and then there's just a 0 here. So 0, 1, 0, 1, 0. So no gates were needed here. I just literally, you don't even have to literally move the wires because you can just interpret each wire being a different value there. So actually multiplying by 2 is ridiculously easy in hardware. It's pretty easy to do in software too, but it's even more easy in software. But yeah, so once you have that, then the reason why we need to have a mux is because we're not always multiplying it by 2. Sometimes we're dividing it by 2, but that's just kind of the inverse. So just figure out how you would get that. Make sure that it's working correctly with kind of the edge cases of negative numbers and that working correctly. But yeah, if you're stuck on if you're not sure how to get the edge cases to work, just build something and see if it works. I think you'll be surprised how simple the solution ends up being. Sometimes that's the best way to approach these problems. Just try something, even if you're not sure it's going to work. And sometimes it just, either gets you to the right answer or it gets you very close that it's clear what you need to change about it to fix that problem. Okay. So yeah, any other, I can hop to project related questions if people have any of those.
Yeah, so this is like super meta question.
Yeah,
it's not even
I
like
love
about the
meta
specific
questions.
project.
Okay,
But
I love it.
I found that so like project 1A, it was the first project of the semester, et cetera, my design was sort of just haphazard and, nothing was really going on and I just sort of went through it.
Sounds about
And
par,
then
yeah.
I was like, oh, this is probably a bad plan because it seems like these things are going to build off each other. And now doing 2A, like my project is like more complicated, I think, because the way I wrote part 1A. And I was just wondering how much more we're going to keep building off these same elements, because like if this assembler that now I'm building for 2A, which like is like mostly working, but is like just the code is just dreadful to read and debug. If we're going to keep using it, I would like rather try to like refactor that now than like dig myself a bigger hole. So I was just wondering how
this is going to be the last version of the assembler that you're writing. Project 3 is going to be doing a simulator for a processor, basically the processor we talk about next week when we talk about pipelining. You're going to write a simulator for that, but you can just you're not going to be expanding your assembler at all. In fact, we'll be providing an assembler that you can use and trust that it's not going to break stuff if you still have bugs in your assembler. So you can do that. And then, project 4 is going to be virtual memory simulator, which is completely different.
Okay, great.
But yeah, I like that you're kind of thinking about that. I think it is, and this was definitely true about me as well. I think kind of more intermediate level programmers, inexperienced to intermediate level of experience, tend to have this fear of rewriting code of like, oh gosh, it took me so long to make this. I don't want to touch it. I don't want to break it. It works now. Let me just keep it there. But like you mentioned, if you are going to expand this in the future, it ends up being way more time to have to deal with your really clunky, hard to understand code than it is to just go back and rewrite it. Particularly, like, I think you would be surprised if you were to go back and rewrite the assembler for project 1A about how quickly you'd be able to do it. Now that you've kind of gone through the mental hurdles,
you could probably do it in
kind
like
of know
10
where you
minutes.
need to go. Yeah, you could probably write it super quick and it would probably be a lot cleaner than the first time you wrote it. So that's something that I've gotten a lot more comfortable with as I've become a more experienced programmer. I'll just periodically go back and be like, you know what, I'm going to have to be using this a lot and I'm going to be modifying it. Let me just go back and rewrite it because this is a mess right now. Make sure you're using like version control and stuff so that if you break something, you can still switch back to it. Test as you go so that if you break anything, you immediately identify it. If you just make a bunch of changes and then test it and it's not working, well, then it's like, well, which of my changes broke it? But if just you make one little change, run your test suite and it's good, well, then you didn't break anything. Make another little change, test it, it's good. Make another little change. Oh, you didn't pass something. Well, let me go back and check this one thing that I changed. So that's, the benefits of having thorough test cases. And again, you don't really need to worry about it for this project because
I was basically mostly just wondering because that one part, my assembler, like from 1A, was just too clunky. And then I started doing this part, and I was like, oh, it's due in 2 days, on Tuesday. So I was like, I don't know if I'm gonna make this less clunky. Let's just work with it how it is for now.
Absolutely.
But like then last night when I was working on it, I was like, oh God, if this hadn't been like this, this would be way better. So I was wondering if I should try to do that before like Friday if we're going to keep using this one piece. But
Yeah. If
we're
it's
not,
working
then
and you're
that's
passing
sweet.
the test cases, that's all we need
All right.
from it. So.
Yep. Thanks.
Absolutely, Jack. Have a good one. Okay, so Norman asking, when do we need to set enable true for registers? So if we set enable true for a register, it means that we're updating the value of that register. So when do we need to set enable? We need to set enable when we have the next result and we want to save that. So the only times that we enable PC is when we have the next value of PC available, which happened in the decode stage. It happens here because on the previous cycle, we calculated PC plus 1. And that's being stored in the ALU results. And now I want to change PC to PC plus 1, so we enable that here. The only other time we enable the PC is at the end of a branch instruction when we detect that this is a branch instruction and they're equal, so we'll enable PC there. And then obviously if we were doing a jump instruction, we would enable it there, but we're not worrying about that implementation. So just think about when we need to update the value. The instruction register, again, we only enable that once, which is when we're first fetching the instruction. So during the fetch stage, we need to update the instruction register, so we enable it there. For all the other states, when we are computing things, we want to hold on to that value so we don't enable it. Does that make sense, Norman? Yeah, and if there's any particular example where you're not sure why we enabled something or why we didn't enable something, definitely feel free to ask. But that's the general rule. Memory is a little funkier because it's not really a register, so enable is both being used for read and write. Yeah. And we don't have an enable for the ALU register because turns out there's no situation where we strictly need to disable it because we can just throw the result away on the next cycle. But you could have added an extra enable for that. It just would have added an extra control wire that's not strictly needed. Any other questions on lecture, projects, homework? What are common bugs on project 2A? So I think probably the most common thing is people just not quite understanding exactly how the format is supposed to be of certain things. So they're having like extra white space somewhere. That comes up a lot. Probably the biggest, more fundamental misunderstanding is people not understanding what is exactly supposed to go into the symbol table and what exactly is supposed to go into the relocation table. I think a lot of people are just trying to like read the rules and implement their interpretation of it without actually thinking about why we're doing this. And if you're thinking about why we're doing this, I think it makes it better because you'll understand the spec more intuitively and it'll avoid these kind of just like common like, oh, I thought this was supposed to go in there. But if you're actually thinking about why are we putting it in there, then it would be clear that, oh yeah, that doesn't need to go in the relocation table. This needs to go into the relocation table. So yeah, the symbol table is used for symbols visible outside this file. And because these symbols are visible outside this file, we want to indicate obviously the symbol, but also where is the symbol located. And so I think a common misconception people are having here, which again, if you're thinking about why we need the symbol table, hopefully should be more obvious why this is a mistake, is they'll have something like BEQ 11 foo, where foo's the name of a section of code. It's a symbol. And this is code location 8. And then code location 10, we have foo. And then it's some add instruction. A lot of people, what they're doing is they're seeing foo here and they're saying, oh, well, I should change this to be capital so that it's external. So a lot of people are going through their assembly and they say, foo, it's got a capital letter, it's global. Therefore, I need to put foo in my symbol table. And I'll say, line 8, that's where foo is. That's where I used foo. But that's not correct, right? Can someone explain to me what's wrong about this entry here? Okay, so yeah, Norman, you're talking about relative offset. So that's good to be thinking about. That's going to be relevant for the relocation table, though. The relocation table is all about what instructions need to change their offset, and that's going to be relevant for branches versus jumps, or not jumps, but loads and stores. Yeah, Kim Bond says it should be line 10 because that's where we define it, right? So what I'm saying here, and again, let's think about why we have the symbol table in the first place. The whole point of the symbol table is that other files can look inside the symbol table and say, hey, I've got this foo call in my code. I don't know where I'm supposed to be branching to. That's where you go and you look in the symbol tables, and then we can look and say, oh, wait, this guy here, he has the symbol table, or in his symbol table, he has foo defined, and he has a line number. So that's where I should jump to in my code. But here, this isn't where we want to jump to in the code, or we don't want to jump here. This is just using foo. I don't care if I'm in another program and I'm branching to foo. I don't care that there's some other branch that you have that's branching to foo. I want to know where is foo. So this is useless information to other files. Line 8, I don't care that other instructions are using it. I want to know line 10. Line 10 is where it's at. And we'd also have the type, whether this is a text or data. This would be text, right? So I think that's a pretty common problem, and again, I think kind of indicative of the fact that people are just trying to implement what the spec says, and they're not really thinking about why are we doing this. And again, the more that you understand the concepts of why we're doing this, I think you're going to avoid these kind of simple. Well, I shouldn't say simple. These are complex ideas, but conceptual mistakes that are very easy to fix once you understand it. Yeah, and if you're failing a bunch of the other test cases, so that would be a good thing to come to individual office hours. I won't be able to look at individual output now, but yeah, the spec example just kind of has a few very basic things that it's checking, but you'll again want to make sure that you've really thought thoroughly about writing your own test cases and just go through the spec. And every time we say you should do this, make sure that you have test cases that are doing different variations of this. And so if you're exposing all of the bugs on our end, that's a good indication that you've done a pretty good job. But yeah, if you're still stuck after that point, if you're passing all of your test cases and your test cases are exposing all our bugs, there are still bugs that, potential bugs that we didn't include in our buggy solutions, which, is intentional because you should still be thinking thoroughly about what other tests you can write. But yeah, if you're still stuck at that point, definitely come to individual office hours and we can take a closer look at your output. Yeah, so again, if we have load word 01 foo, so we're using a global address here, so it's definitely going to go into the symbol table. Any global variable or code segment that we use or define in our file is going to go into the symbol table. The only thing that's going to be relevant is if we've defined it in our file, then it's going to be either text or data in the type section. If we haven't defined it, then it's going to be undefined. But in either case, this is going to be in the symbol table because this is global and it's going to be visible to the outside files. Does that make sense, Norman? Or is there a different reason why you're thinking that it wouldn't be in the symbol table? Correct. Yeah. So yeah, I might have been confusing. So foo is definitely going to be in the symbol table, but again, we're not. The symbol table is not including instructions. It's including symbols. So LW01 is not a symbol. So yeah, that line is never going to be in the symbol table unless we defined a symbol at that line. So if we had bar, then this line would be in the symbol table. Not the line necessarily, but just the label bar and where it's defined. But yes, you're right. We would not include the load word instruction itself in that symbol table. Kim Von asks, if we had the load word line and didn't define foo in this file, then foo is still in the table, but with a U. Exactly. It would be undefined at that point. So we would indicate that we're using this. So we put it in the symbol file, but we're not responsible for defining where it is. We'll have to look in somebody else's symbol table to find out where it is defined. Yes, all global variables that we use or define in this file are going to end up in that symbol table. Whenever a label is used, does it always go into the relocation table? So again, this is where we want to think about what is the purpose of these different tables. Can anybody describe at a high level, why do we have the relocation table? What is it used for? What would go wrong if we just said, we don't need a relocation table? What would be wrong about our assembled linked code at the end? Eleanor says, used to track changes in addresses. Yep. When being concatenated, the linker will need to perform some shifting. Yeah. So if I say initially, I'm saying load word from address 1000 because this right here is, well, I guess I'll just be consistent, say this is at address 10. This is not going to be at address 10 once we link stuff together. If we put files above this might be at line 20 or 30 or 50. So in my relocation table, I'm going to say, because this instruction is going to move, I'm going to say, instruction 7, it's a load word, and it's dependent on foo. And once I link everything together, I'll need to go through each of these elements and say, load word dependent on foo. Let me go find where I relocated foo to, and then I'll go to this line 7 and update 10 to 50 or whatever. So the answer to your question, Norman, is any label that gets used in such a way that it's going to change the encoding after we link stuff together, that's what needs to go into the relocation table. And it's not always going to be whenever a label is used. There are some circumstances where even though we're using a label, it doesn't end up changing the encoding. So you'll need to think about each instruction and how you're using the labels. Is this actually going to change it? Correct. Yeah, that's exactly right. So the encoding, Norman, of add 012 is not changing at all after we link stuff together. Even though it's using the label foo, we don't have to change that code at all. So that will not go in the relocation table. Okay, I think I'm gonna have to step out, folks. Yeah, I'll set up some more individual or group office hours. We'll have plenty of individual office hours for debugging project stuff. I'll probably also try and have a little bit of time if people just want to talk in a group setting about anything, or individual with me about non-project related stuff. But yeah, good luck with project 2A. We'll be posting any additional office hours on the webpage soon, so keep an eye on that. Yep, thanks everybody. See you, Kim. See you, Eleanor. Oh, this was not recording. I wonder when that stopped recording. Well, figure that out.